All right, ladies and gentlemen, so what we're going to do now is we're going to take a look at how the other systems ought to work here. Our current, time system, we use 24 hours, split up over two 12-hour sort of half days here. So what would happen if we tried something else? So for instance, let's say that instead of saying with 12 hours on a single clock face, we have 4 hours on a clock face here, right? We have a planet here whose day is 8 hours long as opposed to the 24 we use. But their noon is at 4, their noon is at 4 p.m. and midnight's at 4 a.m. So let's see what's going on here. Which means, well, let's see here. Now, the first thing to note is that it's going to be changing significantly, right? We're still going to have 360 degrees, but now there's only 4 hours in the clock face here, right? A single clock face is 4 hours. So we know this is going to be now 90 degrees an hour here. So basically what we want to do is that each of these interior angles here is going to be 90 degrees. Well, to be fair, that's actually not going to be that bad to calculate, right? Because 90 degrees, we know what to do with that here. We just basically have to construct 4 90-degree angles around that central point. So I'm going to go ahead and do that here. Take my trusty straight edge and go ahead and do this here. So I'm just going to go ahead and sketch this here. We can see what's going on. The nice part about it is that we were given the 4 and the center of the circle here. So over here on the opposite side, that's 180 degrees. That's 2 hours away from 4. So that makes sense here for this to be the 2 here. Okay, and now to create the 90-degree angles, well, I just have to create a 90-degree angle here, and that's actually not so bad because we know how to do that. That's just creating the perpendicular bisector thingy here. Now, normally when you create a perpendicular through this line through the point, you're going to need a arc here. How convenient that I have an arc like this already. So in fact, I already have 2 intersection points, 4 and 2. This this circle actually did half the construction for us. So all I have to do is just make sure that I have the right. I can construct a perpendicular here, so which means I need an arc of some length here. And I also need another arc of the exact length here from 2. So we can do the same thing, like so. And now I've got my intersection point here, so I can go ahead and construct this piece, like so. And now we can see here that this is our other points here, right? So we had our 2 on the bottom here, so this was 2. So I guess I'll go ahead and color this in so we can see this a little bit better. And that's our 2, this is our 1, and this is our 3 here. So as you can see, our clock is now complete. We basically have this sort of thing here. So now we note that we can go ahead and, so the problem now what we can do is we can connect these points in here with the compass and straight edge. So let's go ahead and do that here. So we can go ahead and connect each of these with the compass and straight edge in order here. So I'll do 4 to 1, 1 to 2, 2 to 3 here, and 3 to 4. Okay, so we have ourselves a blue quadrilateral here. And that looks pretty good, right? I think you can kind of see this here. Now, note that this is a blue quadrilateral here. What sort of quadrilateral is this? Well, certainly it looks very square-like, but can we show that it has to be a square? Okay, so let's do a little bit of analysis here. Now, according to our construction, right, we know that all these angles, 104, 102, 302, and 304 are all right angles here, so that's good. Okay, so let me see here. Let's see if we can figure out what's going on. Well, there are a couple of other things we note here. So this is a quadrilateral with perpendicular diagonals. It's a good sign. Furthermore, this is a radius, so we know 03, 01, 04, and 02 are all the same. So that means we have this sort of thing here where we have perpendicular diagonals, and also the diagonals bisect each other. So we know for sure this is at least a parallelogram, right? The diagonals bisect each other. Furthermore, we have perpendicular diagonals, so this is at least a rhombus here. So now all we have to do is show that this has to be a square. Well, this isn't too hard, right? I think we can probably figure out the measure of some of these angles here. This triangle, 403, for instance, right? There's a 90-degree angle. We got two congruent sides here. 403 is an isosceles triangle. There's a 90-degree angle at the vertex, so that means each of the other angles is 45 here. So there's a 45 and a 45 here. Similarly, we can do the same thing with 302 and find this is 45 as well, and this is 45, and we know that there's a right angle right here. So now this is a rhombus with a right angle, so it has to be a square here. So note how in this situation here, we actually managed to find that this object here is a square. So one thing to note about this here, and I'm going to be using some terminology in this sort of thing here. So in this situation here, I'm going to go ahead and write this out. We say here the square is what we call inscribed. in the circle. Notice that the circle here is essentially a circle that goes through all, so note that the circle hits all the vertices of the square here, so it runs through all of these points here. Furthermore, in addition to hitting all the points here, this is the smallest such circle, right? This is the smallest such circle that hits this. So in essence, we have trapped the circle in sort of like a tiny bubble here, right? So the square is going to be inscribed in this sort of fashion here. It's going to be inscribed inside the circle. We mentioned this here, right? So passes through the vertices of the square. So this is just terminology here. I want to mention this idea of what is known as the square is inscribed in the circle. You know, and again, this is just a matter of opinion. If you're the square, you're trapped in the bubble. If you're a circle, right? The bubble that is the circle. If you're the circle, you've trapped the square inside you and you feel great. So from the circle's perspective, it's trapped the square inside of it. So we can say that the circle is circumscribed around the square. So but notice that both of these things here are justified by the same reason. They pass through the vertices of the square here. So we kind of have this sort of thing. This is our setup here. Okay, so we refer to this idea here. This thing is known as a circumcircle. So notice I've actually described here, we can talk about this circle here. This is known as a circumcircle. So circumcircle here, the most important thing, again, it passes through the vertices of the polygon. Now, it doesn't necessarily have to be a polygon. It could be whatever other things you have. You can inscribe it around something else here about a set of points. But in general, polygons are going to be sort of the thing we'll look at here. So this is known as the circumcircle of a square. Now, a question you may want to ask yourself is, does every polygon have a circumcircle? And the answer to that, the very brief answer to that is no. You should be able to show fairly easily here that there will be certain quadrilaterals that you can't draw a circle around. So you can actually define this idea down here. So you can go ahead and fill in the notes down here about the circumcircle and the polygon here. Okay.